Okay, so we're going to kind of step away from the driving forces for a minute. We're going to talk about what happens when you have reactions that take place in solution. What that means is, generally speaking, dissolved in water. Okay, and almost everything you guys have done so far have been dissolved in water. Certainly acid base are dissolved in water. And what happens is, anytime you have an aqueous ionic compound, remember this means soluble, and you have the solubility rules. If you use the solubility rules and it is aqueous, when it goes into solution, it really doesn't exist as a combined thing. So for example, I'll use the most obvious example is NaCl. That stuff, when you put it in water, it becomes aqueous. All right? So it's salt. It's table salt. Everybody knows that. When you put it in water, it really doesn't exist as one thing. What it does is exist as Na1 plus and Cl1 minus. It kind of undrops and swaps itself. And so that's what happens. That's what dissociation means. It breaks apart into the ions. And they have the ability to conduct electricity. This is why swimming in the ocean when there's a lightning storm, very, very bad idea. They are called electrolytes, and things that are strong electrolytes conduct well. We'll probably do a demo for you on this. Weak electrolytes don't conduct very well. A good example of that is vinegar. Vinegar is acetic acid, and when you put it in water, it breaks apart because it is an acetate, and all acetates are aqueous. It breaks apart into these guys, but they don't get a whole lot of them. It's what's called a weak acid. And it doesn't break apart into a lot of those, and so it doesn't conduct electricity very well. Compounds that are insoluble, that means solid, in water, are not electrolytes, and they don't dissociate. They do not conduct at all because they will not dissolve in water. They won't conduct as a solid. Even these guys don't. Salt won't conduct as a solid. It has to be either melted or dissolved in water. All right, so now we're going to talk about molecular equations versus complete ionic equations. So a molecular equation, this is what you guys have been doing so far. Everything is combined as dropped and swapped. Okay? Everything's a compound. Okay? Everything you guys have done so far have been that. A complete ionic equation, and I tell this to my AP students, a complete ionic equation is a complete pain in the neck. Because it really is. What it does is it breaks apart anything that is aqueous into the ions of which it is made. Okay? That means you are going to be undropping and unswapping everything that's aqueous. Okay? So anything with AQ afterwards is broken into the ions, undrop and swap. Anything that's a solid, a liquid, or a gas, you keep together. So, generally speaking, when you're doing this, you're going to have one of those. You're possibly going to have three of the other ones. So, just saying. Okay, so I'll give you some examples. A molecular equation looks like this. Take two things of salt, one thing of lead nitrate. They are both dissolved in water. This is my solid. Okay, you guys did this in the lab earlier. I believe it is a bright yellow solid. Okay, but this stuff, the NaNO3, did not dissolve. It's a complete balanced equation. It includes the phases. Everything's been dropped and swapped. Lovely. Okay, when you break it apart into a net ionic equation, or a complete ionic equation, anything that has an AQ gets broken apart. So the two NaCl's got broken apart into two Na pluses and two Cl minuses. So sorry I got interrupted. I don't know where I left off. But basically the idea is, has an AQ afterwards, this 2 distributes, two Nas with a plus sign, two Cl's with a minus sign. Technically, you should write a little AQ afterwards, but it's kind of implied by the fact that it has the charge. So if you write the charge, you can skip writing the AQ 8 times. Okay? The PbNO3 is aqueous, so it breaks apart into one Pb, and then that 2 distributes, and you get two NO3s. And again, if you leave the charges on there, you don't have to write the AQ afterwards. But notice I kept this together. And that's because it is a solid. Okay? Solids stay together. But then again, this one distributes. Because it's aqueous, you get two Na pluses and two NO3 minuses. That is a complete ionic equation. I'm going to erase the ink, and I'm going to show you the next one. Okay, this one is an acid-base reaction. So, again, aqueous, aqueous, liquid, aqueous. All the phases are correct. Everything's been dropped and swapped. Everything's been balanced. It's beautiful. Now, taking it apart to the complete ionic equation. Anything that has an AQ breaks apart. I get 1 Mg and 2 OHs. I get 2 H's and 2 Cl's. And again, as long as you include those charges, it's implied that they all have aqueous written afterwards. So all these guys are aqueous. Okay? Now I'm looking at my liquid water. I left that together because it is a liquid, just like I leave together the solid. Those stay together. Liquid and aqueous are different. Liquid means it doesn't have anything else in it. It's a pure liquid. Aqueous means it's dissolved in water. It's a mixture. And so here, this one breaks apart into one thing, and that breaks apart into two things, so Mg2 plus and 2Cl minus. Anything that's AQ becomes a positive or negative charge. Okay, you break them apart. You undrop and swap them. Oh, I got one more on here. Good heavens. All right. So again, completely balanced. Everything's lovely. Here's my solid. Okay. And that's the only one that's solid. That means everything breaks apart. 1 Ca, 2 Cls, 2 Ags, 2 NO3s, 1 Ca, and 2 NO3s. And I do want to point out, it doesn't break apart into atoms. It breaks into ions. That means it breaks into the names, if you want to think of it that way. It breaks apart into calcium and chloride, silver and nitrate, calcium and nitrate, okay, magnesium and hydroxide, lead and nitrate. So it breaks apart into the names or the ions if you want, okay, not the atoms. So a net ionic equation is a shortcut version. These are okay. It shows only the substances that change. That means goes from aqueous to solid or aqueous to liquid. So anything that is aqueous as a reactant and as a product didn't do anything. It just sat around and watched. And they called spectator ions. They don't do anything. They're not reacting. They're not forming a solid. They're not forming a liquid. They're just floating around in solution, la, 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 sitting on the beach kind of thing. So net ionic equations remove the spectator ions from the equation. In other words, you just keep anything that changed. That's all you do. Okay? Aqueous on one side and either a solid, a liquid, or a gas on the other. So, and it only applies to acid base and double replacement. We're not going to do it with the other kind. So, molecular equations, give you an example. Here's the one that we did earlier. A net ionic equation means I'm going to keep this, and then I'm going to keep anything that turned into it. So in here and in here, what things turned into it? Well, the Pb2 plus turned into it, not the nitrate. Nitrate didn't turn into the solid. And 2 of the chlorides turned into it. And so that's how you know. You look at what forms your solid, and you keep that stuff, and you keep your solid. So if I look at this one, I'm not worried about the solid this time, I'm worried about a liquid. Okay? And I'm going to look at the things that made the liquid on my reactant side. That would be OH and H. Okay? And so if you wrote it this way, it's 2 OHs, because there are 2 of them here, and 2 H's makes 2 waters, or you could write it as H plus and OH minus makes water. You could divide everything by 2. That would be okay also. Okay? This one, here's my solid. The stuff that made it is 2 of the Ags and 2 of the Cl's. It makes 2 of the solids, and again, you could divide everything by 2 as well. Okay, so the net ionic's a little bit easier. So, quick summary. Moleculars, basically what you've been doing so far, everything's combined. A complete ionic equation shows everything that is aqueous as individual ions based on their name. So sodium sulfate, sodium and sulfate, not atoms. Net ionic equations take out spectator ions. Those that are aqueous on both sides, they keep anything that changes. Okay, keep any solid, liquid, or gases, molecular times substance. It's only double replacement, acid base. We're not going to do it with combustion, synthesis, single replacement, and double replacement, or decomposition. So let me give you a couple. We're going to do this one. Okay, first you need to figure out what the product is. Okay, it's double replacement. It's not acid base. This is an acid, but that is not a hydroxide, so it's not an acid base. Ba and H are going to trade places, keeping in mind that the 2 came from the charge on the Ba and that 2 came from the charge on the sulfate. My products are BaSO4 and H with Cl, both of which have a 1+ charge on these guys, and both of these guys have a 2 charge. So balanced, it looks like that. So since it's double replacement, what I'm looking for is I'm looking for a solid. There's my solid. So my complete ionic equation is 2H plus, breaking it apart, plus an SO4 2- plus a Ba2 plus, break that one apart, 2Cl- goes to BaSO4, keep it together because it's solid, 2H plus and 2Cl-. So the net ionic equation, I just do it this way. I say, all right, here's my solid. Everything else was aqueous. The only things that made it up were the Ba2 plus and the SO4 2-. Keeping in mind, the order in which you write stuff on the left side of the equation doesn't matter, and the order you write the stuff on the right side doesn't matter. Just matters whether they're reactants or products. Okay, so now I'm looking at this one. And I think, all right, again, I see a hydroxide. This is not an acid. So it's not an acid base. Again, it's a double replacement. Al and Na are trading places. Keeping in mind, oh, that should be a 3. That the 3 belong to the Al and the 2 belong to the SO4. So when I drop and swap my products, I get Na2SO4 and Al, and again, put parentheses around that OH, 3. One of those has to be a solid. This one isn't it. This one is. So my complete ionic equation is everything that's aqueous on both sides, I break apart. So I have 2Al3 plus and 2, I read that wrong, 3SO4 2-. I didn't balance this, did I? Let's put a 2 here, and a 6, and a 3. There we go. 6 Na plus, 6 OH minus, goes to 6 Na plus, 3 SO4 2-, and 2 Al OH 3s. For my net ionic, I'm getting rid of the sulfate and the sodiums. So I got 2 Al3 plus 6 OH minus goes to 2 Al OH 3 with a solid. Okay, these are hard. The complete ionics are really hard. Okay, go ahead and see if you can do these and stop the movie, and then we'll start it up again and go over. Okay, so I'm looking at this one. I see acid. I see hydroxide. Ah, yay! Acid base makes water. And the Mg goes with this guy. Mg has a charge of 2. C2H3O2, 2. This is liquid water. Balance it by putting a 2 and a 2. So that's the molecular equation. Complete ionic equation is 2H plus 2C2H3O2 plus Mg2 plus 2OH minus makes 2 water, which I keep together, plus Mg2 plus and 2 acetates. Okay, net ionic, always the best one. 2H plus 2OH minus makes 2 waters, done. Or you can get rid of the 2's. Okay, here, double replacement Pb and Cu. My products are going to be Pb, Cl2, because that 2 belongs to Pb, and that 2 belongs to Cu, and Cu, NO3, 2. This one's my solid. Balanced, it's already balanced. So my complete ionic, break it apart. Anything that's aqueous, I got Pb 2 plus 2 nitrates plus Cu 2 plus 2 chlorides goes to PbCl2 solid plus Cu 2 plus and 2 nitrates. Nitrates are gone, coppers are gone. My net ionic, Pb 2 plus 2 Cl minus PbCO2.